Hello and welcome to the 7th session of Maths and Ideas with Reza Negarasani. I'm going to pass the mic off to him now.
Okay, hello everyone. So can you hear me? Because everything went silent suddenly. Okay, good. So we continue with Euclid's. I can't hear myself. Someone is not muted. I think it's you. Okay. So we continue with Euclid's elements, and hopefully we go over a couple of more demonstrations, and then I talk about some of the more, like, analyzing some of the and cons of Euclidean system, and gets a little bit into the mathematical conceptual structure of Euclid's elements. After that, if there is time, I will move to a rather introduction to a new topic to use in the following sessions, and that's the correspondence between analytic geometry and particularly the study of mechanical machines. I will talk a little bit about this correspondence between geometrical problems and mechanical problems, which will prove useful when we get into a study of Urim's diagrams and the invention of mathematical graph and discovery of uniform acceleration, and how Urim solves these problems via going back and forth between mechanical machines of the medieval age and analytic geometry handed down to him via Greek tradition. So before starting, any questions, any philosophical discussion, mathematical discussion from previous session? Jake, you were looking at me.
I wanted to give, so this is like, this jumps back to, I think, to the analogy of the divided line. But I was reading the epistemology of the divided line analogy and sort of getting to the issue of where the mathematicals go in the allegory of the cave. And so he gives like one explanation, which is that the mathematicals fold into the idei and are just, and rather than being something that that separately mediates between the smaller line of CE and the idei, is actually just a particular way of training oneself to start to perceive them. And I was wondering if we could extend that point in the allegory of the cave to say that, like, when you set up this, when you construct this setup where you have objects producing shadows as seen by people in a particular set of positions, and you've coordinated these elements within the cave to produce a particular, like, optical illusion, there's math in there. Like, someone had to have understood the process by which objects can generate appearances via the geometry of the interaction between light, shadow, and the eyes of the prisoners and so forth, is like sort of the coordination of the relationship of objects and their images, so of the second smallest and smallest portions of the line. Could we say that encodes or enfolds the mathematicals on the side of the sensible in the same way that the sort of learning ratiocination on the side of the ideal enfolds mathematics into understanding?
Did you watch the previous session when I had a brief comment on and the role of mathematics and mathematical entities in the divided line.
Yes. Yeah, I was talking.
Okay. Yes. Okay. So the thing is that you know what Jake is talking about is, I mean, just because the analogy of the divided line comes right before an allegory of the cave, this doesn't mean that the divided line has anything to do with the allegory of the cave. But in fact, it does. Analogy of the divided line is simply what you might call to be the transcendental ladder, the diagrammatic scheme of escaping from the cave.
Right. And so I'm talking about the Nicholas Rescher on the epistemology of the divided line, where he talks about this at the end. And I don't know, the problem
I
that's...
have read that.
Say again? Can anybody hear me?
I can hear you. I think Rez's signal is pretty spotty right now.
Yeah, I can.
Can you hear me now?
Yes.
Jake?
Yep.
We can hear you.
Okay.
The signal's a little spotty though.
This is strange because I can hear you really well.
Oh, all the way through that?
Reza, can you try talking right now? Oh, maybe not. It's frozen again. Reza, can you hear me right now? If you can hear me, it might be better to log out.
Sorry, go ahead.
It might be better to log out and come back in, and then try lowering your bandwidth. Oh, never mind. You're back. Okay. Hi.
Hello. Okay.
Could you? Reza, can you lower your bandwidth to maybe just the very low?
How can I do that?
Up in the top bar where it has all the icons of like the hang up button and video button, there's the triangle of ascending bars. Just click on that, and then it should drop down to a scale where you can lower to either audio only or high quality bandwidth.
I can't. Where is it exactly? The
It
triangle.
It should be at the top of the Hangout box. So as you go to the top, there's like maybe 7 or sometimes there's 6 buttons up there.
You mean control room?
No, no. Well, it's on the top of the window, not at the left-hand side.
Oh, okay. Adjust bandwidth usage. Okay.
Yep.
So
And then
what should I do?
Go to very low.
Go to the very low.
Okay. Is that, can you talk now? Oop, maybe we lost you now. Hello?
You?
Okay, it still seems a little spotty, but okay, you look good now. I think that's okay.
Okay. So in response to Jake very quickly, is that mathematics is essentially which they interact, they produce multiplicities, but also unifications. Huge, commentaries have been written on this idea of what the principles are and how mathematics do basically these principles. So when I'm talking about the one, and for example, the infinite delta, I'm not talking about the number one. I'm talking about simply a what you might call to be a metaphysical law in Plato. Number one is in the domain of mathematics, whereas oneness is something that is neither ideal nor mathematical. It is simply a principle, what you might call to be the principle of integration and disintegration that allow, in the analogy of the divided line, for us to have multiplicities and identities, differences and sameness. Now, I don't want to get into the details, but precisely because mathematics is generated by these principles, it has an intermediary within the analogy of the divided line. And it's intermediary in the sense that it is immutable, it is fixed, hence it has something of the ideals in the divided line, namely the last segment, but it's also multiple. So you have multiplicity of structures, of mathematical structure, and hence it is also something of the sensible, of objects. So precisely because of this, being at the same time has something, mathematics both enjoys some of the attributes of the ideals or idols, and enjoys some of the attributes of a sensible realm. Because of this, it's enjoyed very special metaphysical status in Plato's analogy of the divided line, in the sense that mathematics, understood broadly, can be seen as a model that mediates between the forms, the ideals, where there is a domain of reason, dialectical reasonings, and the domain of the sensible. And also, one more thing is that when we are talking about, and precisely when you compare analogy of the divided line with the allegory of the cave, you see that as soon as you start to see this connection in terms of mathematical structures, the object casting shadows and the optical illusion, you have already diverged from pure sensibility and pure empirical facts in the domain of objectivity afforded by you, via mathematical models. But of course, mathematical models are what you might call to be inferior within the analogy of the divided line to the ideals, insofar as they are, and the inferiority of them is precisely because of the transition between particularity and universality. Whereas in the realm of ideals, the realm of pure forms, all we have is unconditional universality, what you might call to be the pure transcendentals. So I don't know if this answered you, Jake, but nevertheless, I will hopefully, when I'm teaching the next course on Plato, I can make this far more clear. But also one more thing that you need to have in mind when looking at the analogy of the divided line, it's simply not just an epistemological model within Plato's work. It is a model, an analogical model that glues metaphysical, ontological, and epistemological and ethical problems in Plato's Republic. So it's basically the diagram, not just a diagram. The diagram of the entire Platonic thing.
Okay, cool, thanks. That definitely helps me at least refine my question. I need to go and sort of look at the end of that paper again, and then I'll maybe post a better version in the classroom. Thank you.
Sure, sure. So let's just start with our problems. We went to the parallel postulate. We now I think it's time to look at a little bit more into the idea of a parallelogram. Just parallelogram, something that will come across when you're talking about a linear algebra and a scalar products. Put the air. Hello?
Hi, the signal's pretty spotty. I'm going to ask if all the students can lower their bandwidth. That I'm not sure if that helps, but might as well try right now.
It seems that even the iPad doesn't go through. So maybe instead of doing outright just going to the idea of parallelogram, we should save it when we get to the idea of and stuff. And I start analyzing some of the stuff that we have been talking about, Euclid's diagrams, and maybe if the connection gets a little bit better, we switch to iPad. Sorry for this. I probably at some point I need to get a whiteboard so I can, write this stuff on whiteboard. So we talked about, when we were talking about Euclid's elements, particularly when we came across common notions, where basically, for example, it was saying that the whole is always greater than its part, two things that are equal to one thing are equal to one another. we mentioned something called exact and co-exact properties of the diagrams in Euclid's elements. Now I'm going to talk about a little bit about these exact and co-exact properties, which basically sheds light on exactly the inferential licenses that the diagrams in Euclid systems can afford us. So I mentioned that the 5 postulate express in elements, the first 5 postulates express facts about geometric configuration. For example, what is exactly a circle, what is a triangle, so on and so forth. But the common notions express facts about magnitudes. Magnitudes, you might say, they are objects that can be compared, added, subtracted, provided they are of the same kind. Now, this idea, the entirety of information afforded to us by diagrams in Euclid's elements has something to do with precisely how these magnitudes are compared to one another. Now, equalities and inequalities, for example, greater and less, among objects distributed throughout the diagrams are of great importance in Euclid elements. An inference principle for both are available within the discursive text of the book. In order to allow these notions to function also in a diagram-based geometrical argument, the elements makes it first order of business to secure transfer around the diagram so that the direct comparison may be made, both so that inequalities already available in the discursive text may be realized as proper inclusions in the diagram, and so that inequality the diagram may be related to explicit inclusion there, which then may be read off or made explicit. Roughly speaking, co-exact attributes are those conditions which are unaffected, and this is Mander's definition, Kenneth Manders, who first started to look at precisely the kind of information that diagrams in Euclid afford us, exact and co-exact information. Now, in Manders' word, co-exact attributes are those conditions which are unaffected by some range of every continuous variation of a specified diagram. Paradigmatically, it includes another, which is unaffected, no matter how the boundaries are to some extent shifted and deformed, or the existence of intersections, points such as those required in Euclid proposition number 1. Now, in a more rudimentary way, exact relations are the ones applied to the comparison of magnitudes, hence the idea of co-exact. Exact entirety of proofs involve co-exact, where we basically construct, manipulate the given diagram, the given datum, in a way that it allows us to compare the information, magnitudinal information, with one another.
Reza,
For example,
can you repeat that, just that last bit? Sorry, we lost you a bit.
sure. I was saying that the majority of Euclid's elements involve to be co-exact information, namely the constructive comparison between magnitudes. For example, you remember how you constructed an equilateral triangle, where the radius of a circle was constructed so as it constitutes a side of a triangle, allowed us to make a comparative analysis of what it means to be a side of a triangle, a magnitude as such, magnitude 1, and to be at the same time a radius magnitude 2. Or for example, you remember last session when we were talking about how we have been given a line segment and a point outside of it. How from this point can we draw a line segment that can be said to be equal with our given data, namely our line segment. And Philip said that we use the compass and open it size of our line segment and transpose the compass onto the point outside, we create a new line. But then we discussed about this idea that in Euclid's element, this is an illegal move. Precisely because there is we should not anticipate that when we have the vehicle first, that we have the vehicle of such a transfer, nor that throughout the process of transferring the compass, the size of the compass, namely the distance between two arms, will be preserved. These are intuitive anticipations. That doesn't mean they hold into the quasi-formal system of elements. So we had to invent a diagrammatic proof that allow us to construct such a new line segment that can be said to be equal to our given line segment. So if you remember, we drew.
Oh,
go on, Philip.
So what I was going to say is, so there are no numbers in Euclidean geometry; they're just lengths. And
the lengths are represented by ratios in Greek geometry. Right. Yes.
And you can't lift the compass off the paper into another plane and put it somewhere else. So what you have to do is by figuring out ways to compare magnitudes by making continuous drawings built on whatever lines or points you have, so that you're not entering that plane and re-entering at another point, as you do later when you're talking about transformational geometry and
absolutely brilliant. Yes, that is so. Basically, what you are getting is that you might say that co-exact information are about how variations range over a continuous given set of data. For example, your idea of a plane. Precisely because, for example, and what is, for example, in the diagram example that I made, creating a new line segment that can be said to be equal to our given line segment, what is exactly the geometrical configuration that allow us to carry out the construction and making explicit of these coexact information. It's a circle. If you remember, we drew two circles, and these circles can be said to be like a copy machines, that they do in the diagrammatic system what we intuitively do given segment of the line into another. So if you remember, it's in fact, whenever you are using a demonstration of a proof in Euclid, circles can be thought as a copy machines, precisely because of this property that the radius of a circle is always constant. So if you manage to construct a circle that has some relevancy with your given magnitude or your geometrical configuration, you can copy it somewhere else. And the same thing with equilateral triangles when it comes to line segments and angles. And we saw that in that demonstration, we dealt with both. Basically, the vehicle of our transfer, the vehicle of ranging over variations smoothly, were two geometrical configurations, circle and an equilateral triangle, that allows us to extract coexact information and carry out with the demonstration. Any question?
And so this is something based directly on the gesture of drawing with the compass and observing that at every point in drawing each point in drawing the circle, the distance between the legs of the compass hasn't changed. And so then you have a brute gestural fact that the radius is constant, and that through using a constant radius, you have produced a circle on the page. And that's sort of the gesture diagram data for natural deduction line of production.
I would probably don't go so far as to call it gestures, precisely because what we are dealing with here, yes, I mean, we can talk about in terms of like diagrams being the frozen avatars of gestures. And for example, in a circle really freezes the gesture of drawing a circle by way of a compass. But with here, if you remember, is a part-whole relationship.
Hey, Reza. I guess we're just going to wait a second and hopefully he'll come back in. Hi, Reza. Can you hear me? The signal's really, really choppy right now.
Can you hear me?
Yeah.
Yep.
Okay. Sorry, I have no idea why the signal is. I mean, I can hear you pretty well at my end. I don't know why you can't hear me. So I was saying that, the diagram in that sense is something more than gesture, at least in Euclid's element, precisely because it is about a certain stabilized particle relationships. For example, between a circle and its radius, between a triangle, its sides and its angles. Hello?
Okay, yeah, no, that makes sense. But this is a process, or this is a process by which those part-whole relationships become something that can be inputted as data into natural deduction, or into.
Yes, and what are exactly in this sense, co-exact data? Co-exact data, as I mentioned.
I'm guessing we lost Reza just now.
Being contained in another thing.
Hey Reza, I think we missed all of that for maybe a minute or more. Sorry, I don't know.
I was saying, let me, 1 second, let me get something. 1 second.
Okay.
Oh.
Hi, we can hear you now.
Okay. I was saying that when we are talking about co-exact information in Euclid's elements, which of course co-exact information in Euclid's elements are covered mostly by common notions. For example, a whole is always greater than its parts. Or, for example, two things that are equal to one thing can be said to be equal to one another. Or, for example, that you can subtract equal amounts from two things that are equal, and that would result in equal amounts or equal magnitudes. Now, the majority of these co-exact information, when you look at Euclid's demonstrations, involve with relationships of containment. For example, you remember in the demonstration of if we extend one side of a triangle, the exterior angle can be is always greater than the opposite, and we saw that the last stage of the proof involved with the idea of constructing a new triangle that is equal to our given triangle. And the angle of one of the angles of a triangle that corresponded to ulterior interior of our given triangle was inside the new external angle, and that was the last stage. But precisely because of this, precisely because whole is always greater than its part, if we have managed to construct a magnitude, a given magnitude, that was our interior angle, we transferred it onto our what we wanted to prove, which was the external angle, and we showed that it is in fact a part of that external angle. Hence, by virtue of the common notion, where we can say whole is always greater than the part, we can say that the external exterior angle is always greater than the positive, the opposite interior angles of a triangle. So we see here a relationship of a containment, part and a whole, that we have throughout the process of construction, even if it wasn't given to us, by way of construction, by way of manipulating the diagram, destabilizing its particularity, we managed to transfer what was given to us, the magnitude, the interior angle, onto our problem, which was the external angle that always should be greater than interior angles of a triangle. And once we did this transferring, then we could make explicit a set of co-exact relationships. You can see in any of the demonstrations, particularly as you move forward in Euclid's propositions, you can see you use common notions a lot. And you can see that these co-exact information basically become more and more prevalent. Comparison of magnitudes, the relationships of containment, rudimentary topological information.
So I really like your notion of it being a quasi-formal system, because of course it's always presented in high school geometry as if it's a purely deductive system, and modeled for thinking logically or something. And it's quasi-formal in the sense that it is step by step. It proceeds from common notions and things that have been demonstrated earlier, like equilateral triangles or parallels, to derive the next notions. But I mean, as you pointed out, certain concepts, or as Hilbert pointed out, things like betweenness or what exactly an intersection is are not defined. Which is why it's quasi-formal rather than formal, right?
Yes, yes. But I would say that Hilbert would say that from a Hilbertian perspective, Euclid's system is in fact non-formal. But once we look into it, that we see that even though it does not have a well-formulated syntax, even though that there are gaps of reasoning when we are manipulating our given datum, there are still inferential classes of inference that we have to follow within the diagrammatic reasoning.
So, but the appeal of Euclid comes from it being a hybrid form.
Yes.
And the attempt to correct its deficiencies is misguided. It's a totally unusual space that is quite congenial to exist in, because you do exercise logical and inferential capabilities, but you're also doing other things that imply diagrams, constructions, and building. Yeah.
Yes, perceptual cues. I mean, as I mentioned, remember that I said that Euclid's Elements needs to be read as a philosophy book, particularly within the context of the ideas that are prevalent in academia, in Plato's academia. And precisely this is what you might call to be the amphibious quality of Euclid's system, tries to confirm the metaphysical status of mathematics as a whole, being a mediator between the perceptual mechanisms in the analogy of the divided line and the realm of forms, pure forms or ideals, which are absolutely formal. So, so when we look at very briefly again, when we look at Euclid's diagrammatic constructions, we discover that if one looks at the elements closely is that Euclid only allows the co-exact properties of a diagram to ground the inference in a proof. To establish an exact relation, Euclid carries out an argument in the text, but from the perspective of the diagrammatic construction, we only deal with co-exact information, rudimentary geometrical topological information that are being enveloped or encapsulated within our common notions. Now, no matter how precise our techniques for the production of a diagram satisfying exact conditions, there will always be a range of variation in what's produced. So Euclid can be understood to account for this by restricting himself to diagrams' co-exact properties that allow us to make these transitions between different variations of a diagram. Because from a perceptual diagrammatic, simple diagrammatic perspective, a triangle as such, any form of diagram that you make is going to be a particularity of the idea of the triangle as such. So if we are going to construct and articulate what it means for something to be a triangle, we need to allow us, we need to come up with a method of extracting certain kind of information that allow us to move or make transition between these particularities of particular individual triangles, through which we can extract the universal information about what it means for a geometrical configuration to be a universal idea of a triangle as such. Hence the idea of, again, what we were talking about, the dialectic between the universal and the particular that Proclus talks about in his commentary on Euclid's Elements. Of course, the soundness of Euclid's co-exact inferences from such diagrams is not always obvious. The construction is always performed on a particular diagram. Though the diagram is representative of a range of configurations, i.e. all configurations with the same co-exact properties, it cannot avoid having particular exact properties. And these exact properties can be seen within co-exact relationships between multiple diagrams, namely variations. When the same construction is performed on two diagrams which are equivalent with respect to their co-exact features, but distinct with respect to their exact features, there is no reason to think that the two results will be equivalent. This leads to doubts that the co-exact relations Euclid expects us to read off of an augmented or manipulated diagram hold for all possible constructions. And there is nothing in the diagram itself to remove these doubts. The main challenge in formalizing Euclid's diagrammatic method then is coming up with rules which license the diagrammatic inferences needed for Euclid's proofs and ensure the geometric generality of all such inferences. The role of a circle as a copy machine. Well, I mean, it's quite simple. We know that circle is defined by its radius, a constant distance from the center to the circumference. Now, precisely because of this constancy of a radius, if, for example, we are given a line segment, namely a given datum, we can always introduce a circle into our construction that can replicate these line segments. So all you remember in the, for example, was it proposition 2, where making an equilateral triangle, we were given a line segment. Now, we are going to copy it if we take this line as a radius of a circle. And precisely because it's the radius of a circle, it has the potentiality to be, if we manage to add a circle to our diagram, to our given diagram or geometric configuration, we are capable of replicating the datum that is given, namely the line segment, onto a different place on our plane. And that's exactly what circle was supposed to do. In fact, we created 2 circles because one circle couldn't produce this result. We created 2 circles, and these 2 circles managed to, like a copy machine, copy our given line segment as the idea of a radius of a circle and transpose it somewhere else. And then once these 2 circles are being drawn, the line segments intersected with one another, namely 2 radiuses of the 2 circles became 2 sides of our triangle and created an equilateral triangle. You have this a lot in Euclid's demonstration. Whenever you see a circle in Euclid's demonstration, think about it as a copy machine. As a copy machine that copies a given line segment, and by virtue of its part-holder relationships, namely the relationship between the circle and its radius, it has the capacity to take this line segment, translate it into a radius, and produce somewhere else within the circle, another radius of the circle. Hence, carrying your given datum within the diagrammatic inference licensed by your particular type of geometrical configuration. Here, a circle. Questions?
So in Macbeth, this is where the issue of pop-up diagrams or pop-up features of diagrams occur. Like in the sense that, for example, given 2 lines that cross or cut one another, Euclid assumes that there is a point at their intersection. And he doesn't, justify this or like require an extra diagrammatic step in order to show it. It's simply that as you go through this process of drawing 2 circles and of deriving an equilateral triangle from them, you have features that appear. Are these the kind of like topological invariances that we're describing as coexact, or do they just depend on them?
Yes, I mean, coexact is precisely what you might think about it. It's a mode, it's a kind of information that a transfer between particularities, between variations. Honestly, we talk has something to do with the Platonic idea of making explicit, making manifest in what is already given. So, and coexact information are precisely these kinds of transfers that can make explicit the relations between your given datum. by transferring them from one geometrical configuration, from one datum to another datum, another geometrical configurations, and pop up, functions. You can say that they are these moments in a Hegelian sense, moments where the relations, the exact stabilized relations between your given datum become explicit by virtue of the right kind of transfer between variations.
Okay, that makes sense. Thanks.
So one thing that we need to know is that even though Euclid's elements is not essentially axiomatic, but we treat it as if, in the Kantian sense of as if it was axiomatic. This as if, precisely in the Kantian sense of as if, is not ever constitutive, but it's about what we can realize out of what has already been given to us. So it's this axiomatic approach to a quasi-formal system that, even though it is not axiomatic, we treat it as axiom, is no longer can be said to be constitutive, in the sense that we usually deal with axiomatic systems of mathematics, in which the role of axioms are constitutive. In Euclid's systems, we can treat it as axiomatic, but no longer in a constitutive sense, but in the transcendental sense, in the sense that we can say, as if the system was axiomatic, then we could build such and such constructions. And this is perfectly fine in understanding Euclid's system as an axiomatic system in which axioms are not constitutive. They don't have pure logical, well-formulated syntax, like pure axiomatic systems of mathematics. But they have transcendental roles. As if it was an axiomatic, then it could create such and such relationships, manifest such and such correspondences or correlations between geometrical configurations. So in this sense, the axioms we choose are not completely arbitrary, because the only axiomatic systems that are worth studying are those that describe something useful or interesting. For example, in our, in Euclid's elements, they are interesting from the perspective of the kind of perceptual cues that they afford us. But from a strictly logical point of view, we may adopt any consistent system of axioms that we like, and the resulting theorem will constitute a valid mathematical theory. But the catch is that one must scrupulously ensure that the proofs of the theorems do not use anything other than what has already been assumed in the postulates. If the axioms represent arbitrary assumptions instead of self-evident facts about the real world or the mathematical structures, then nothing except the axioms is relevant to proofs within the system. Reasoning based on intuition about behaviors or properties that are evident from diagrams or common experience in the real world will no longer be justifiable within the axiomatic system. Now, looking back at Euclid, with these newfound insights, mathematicians realized that Euclid had used many properties of lines and circles that were not strictly justified by his own postulates. Now, let's examine a few of these properties as a way of motivating the more careful axiomatic system that is, hallmark of modern mathematics, as in contrast to Euclid's system. The first one, I don't think that I can turn on the iPad. I'm afraid of losing the connection again. So you remember the much discussed Euclid proposition in book 1, constructing an equilateral triangle. We have been given a line segment. We use the compass, open the arms over the compass with the same size of our given datum, namely the line segment. Now, we put the compass on one end, we create one circle, we put the compass on the other end of our line segments and make another circle. Now, from the perspective of Euclid's postulate, what is already given to us, the givens, the datum, there is no reason for us to anticipate that these two circles that we have created, thus and so, are going to intersect, hence creating a triangle, an equilateral triangle. So this is merely a convenience, and is not meant to suggest that points take up any area in the plane. It seems obvious from the diagram of creating an equilateral triangle, that there is a point where the circles intersect. But which of Euclid's postulate justifies the fact that such a point always exists? Nowhere does Euclid give us any justification for asserting the existence of a point where two circles intersect. Of course, I know that Danielle Macbeth thinks of this as a function of a pop-up. The apex of your equilateral triangle created by the intersection of the two circles, Macbeth treats it as a pop-up function. But this pop-up function, we can only see it as a pop-up function, see it as the concept of a pop-up function, if we had already filled in the gaps of Euclid's postulates, anticipated that these two circles do in fact intersect. But as I said, there is no information already given to us that can be said to be a justification for asserting the existence of a point where two circles do in fact intersect in this demonstration. Another one you remember in our proposition 16,
And what was the proposition 16? In any triangle, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angles. The one that we demonstrated last session. And this proposition is called nowadays exterior angle inequality. We talked about that it's probably one of the most clever and elegant demonstrations in Euclid. From looking at it in the first glance, it's not easy to see where the gaps are within this demonstration. But there are at least two gaps inside this demonstration. Now, after, you remember that, so we were given a triangle. We extended one of its sides, and then we would say that the external angle is always greater than the interior and opposite angle. To demonstrate that this is really the case, let me get a pen now that I can't turn on the iPod and draw this for you with a pen and a marker. 1 second.
So I have a basic question for the class, and if this derails the conversation, we could just wait. But if we can't imagine a point when we, through the process of drawing two circles, it seems like that undermines the whole idea of like diagrammatic construction, because that seems, I don't know, what do other people think? Like how would you then, the process of a circle being drawn from the given data, the line segment?
I mean, that was kind of what I liked so much about, at least what I understood Macbeth to mean by a pop-up function, was that there is this topological invariance in the process of sketching or of constructing circles on a single plane, which forces the emergence of an intersecting point before we would necessarily have any prior concept of it.
Right.
And to me, that's sort of like, that's a validation of the constructive process, because the constructive like a validation and an explanation of the way it relies on the topological constraints of its medium to produce new elements of knowledge.
Right.
So this was our, if you remember, our diagram, where we extended a line from B, cutting the side AC at its midpoint, and then extended BE to point F, where BE and EF can be said to be equal. So we extended BE and produced EF. Both the same equal size. Now, from now, once we look at it carefully, after constructing the midpoint E that bisects the side AC, Euclid then extends BE past E and uses proposition 3 to choose point F on that line such that EF is the same length as BE. Here is where the first problem arises. Although postulate 3 guarantees that a line segment can be extended to form a longer line segment containing the original one, it does not explicitly say that we can make the extended line segment as long as we wish. As we mentioned, if we were working on the surface, that wouldn't be our given surface, our given plane, what Philip mentioned when we were talking about this in terms of making given a line segment and a point out, we have to use a circle rather than just moving the compass, because that's, we do not know if once we do that, we enter another plane. Now imagine, for example, that this is also the case here. Imagine that in fact we are not working on a regular plane, but we are working on the surface of a sphere. Try to construct and demonstrate this diagram on a surface of a sphere on a different plane. Now, extending BE to EF wouldn't be possible on the surface of a plane, because great circles have a built-in maximum length. Let me show you what would happen if we were constructing this on the surface of a plane. That how F behaves. This would be the case if we were using, if we were constructing this diagram on the surface of a sphere.
Can you raise it up just a little bit? A little lower? Sorry, right, just a hair more up. That's good.
Is it good?
That's good. We can see it.
You see where F ends up to be. Now, the second problem arises toward the end of the proof when Euclid claims that the angle ECD, the angle ECD is greater than the angle ECF. ECD is greater than the angle ECF. Now, this is supposed to be justified by common notion 5, which is whole is always greater than a part. However, in order to claim that angle ECF is in fact a part of angle ECD, we need to know that F in fact lies in the interior angle of, in the interior angle of in the interior of angle ECD. Now, this seems evident from the diagram. There is nothing in the axioms or previous propositions that justifies this claim. To see how this could fail, consider again that we were constructing this diagram on the surface of a sphere, which I did, with A at the North Pole and B, A at the, you see, A at the North Pole and B and C both on the equator. If B and C are far enough apart, it is entirely possible for the point F to end up south of the equator, in which case it is no longer in the interior of angle ECD. Now, let me, just how to visualize this more intuitively, let me just draw this in an unwrapped plane. So, as I mentioned, can you see this?
Yes.
Okay. So, if I unwrap the diagram constructed on the surface of a sphere, if we see that's according to common notion 5, the whole is always greater than the parts. We are supposed to show that ECF is within, ECD is within ECF, these two angles, hence showing that the external angle ECD contains the angle ECF, and ECF corresponds to either the interior or opposite angle of the triangle, a coexact class of information that we managed to extract via manipulating our diagram. But in order to claim that the angle ECF is part of angle ECD, hence demonstrating the proposition, we need to know that F lies in the interior of angle ECD. Now, this seems, as I mentioned, evident from the diagram, from the perceptual encounter with the diagram, but from the class of inferences afforded to us by common notions, by the propositions and the postulates, there is nothing in the axioms or previous propositions that justifies this claim. Precisely because we can construct this diagram so that F is no longer in the interior of angle ECD. Namely, ECF will never be within ECD. The part, what we taken to be part of a whole, will never be a part. Now, there are so many of these examples in Euclid's Elements, and of these kinds of gaps. And these gaps are precisely because we are dealing with a quasi-formal system. And interestingly enough, people like Lobachevsky, like Riemann, the people who basically moved to non-Euclidean geometries precisely looked at these gaps to see what kind of information might be introduced to these gaps. And if we could find what these gaps are really about, could we move out of the Euclidean system or not? And that was, one of the main motivations behind the conceptual development of non-Euclidean geometries. Exactly determining the nature of these gaps and the kind of information that we can come up with that could coherently cover up or fill in these gaps within Euclid's elements. Now,
can you explain a little bit what exactly you mean by gaps? It sounds like what you're saying is like, we have these principles of construction, and as we execute them, they have these hidden premises about the way that they function. So the implicit assumption was that we were constructing on a flat plane rather than some other type of topological space.
Yes, that's exactly by gap I mean like that. That there is an assumption that is always already talking about an unwrapped flat Euclidean plane, even though we haven't seen this assumption being made explicit or being contained within any of the previous axiom or propositions that we have dealt with so far in constructing or demonstrating this proposition. Now, once we, as I mentioned, the idea of the givens or the datum is something what you might call to be truth candidates. So truth candidate means that we have to create a theory, a system that only uses these truth candidates as building blocks of constructions. It should not smuggle in any hidden assumptions that wasn't explicitly contained or expressed by way of these basic truth candidates or given datums. If we do that, we basically move toward what you might call to be non-formal systems. Now, it seems that the development of non-Euclidean geometry can be seen as an inquiry into the non-formal aspects of Euclidean geometry in comparison with formal aspects of proper axiomatic systems of mathematics that allows us to determine what are exactly the sort of information that are missing within the Euclidean system that make the system non-formal. And these are what you might call to be the gaps. Once we identify these missing assumptions or information, then we are capable of finding a solution how they can be accommodated within our systems. But sometimes accommodating this new information require us to move into a different system altogether, rather than assuming that every system that we are, every plane that we are dealing is going to be a flat, which of course this is not, even the idea of a plane unwrapped surface is not explicitly mentioned in our given datum, in our given propositions in Euclid's elements. But imagine that we identify that this is really the implicit assumption. Now, in order to see how the construction can be done, now explicit assumption that this is like a flat plane, we see that we can't really adequately investigate this unless we move we transit to a new system, in a system in which what you might call to be unwrapped flat surface is a special case of a curved wrapped surface, a greater sphere. And this greater sphere basically sheds light both on the implicit assumptions that we had in our previous systems, but also give us new data, new givens, new information.
So this is maybe, I don't even know how to formulate this question exactly, but how would you even begin to move to a different topological space without using the constructive elements that you've been using?
Well, as I said, the first things, what you might call to be a procedure, the first procedure is that identify the assumptions that haven't been explicitly stated within the previous propositions or postulate. But nevertheless, we are mobilizing them blindly so once we identify these, we can see alternatives to these assumptions. The hidden assumption, the implicit assumption was that we are working on a flat, unwrapped surface. Now imagine, but we already know in that geometrical progress of that investigation, people already know that there are different forms of planes, in the sense that they are different from flat wrapped surface. This is already implicit, given to us by Archimedes, hyperbola and a study of the great circles. So once we identify these implicit assumptions, find possible alternatives to these implicit assumptions. You have a flat, unwrapped surface, but also we know that there are non-flat, wrapped surfaces, the surface of a given sphere. Now try to make the same construction or demonstration within these wrapped, non-flat planes, the surface of a great sphere. Once you do that, then you see that the demonstration doesn't hold up. Once the demonstration doesn't hold up, then a mathematician can go on and find a solution, a more general solution that can in fact be said to hold, but within the new basically plane, a plane that can be said to be more general than our flat, unwrapped plane, the Euclidean plane. So it goes in a kind of a, what might call to be a kind of a critical procedure that starts with investigation of the hidden assumption, then transposing this hidden assumption onto a different alternative given to us, what you might call a new set of data that cover different types of geometrical configurations, then a study whether this demonstration hold or not within this new class of entities. If it doesn't hold up, then find a solution that can be more general. And then from that, construct more and go back and forth between your previous system and the kind of system that you are developing. And this is exactly how Euclidean geometry was made, by way of this, what you might call to be dialectical back and forth that started from making explicit of hidden assumptions.
Awesome, that was helpful.
So, how much time do we have?
Class is supposed to go till 3:30, but if we'd like to, we can run a little bit later if you're able, or I'm flexible today.
Sure, sure. So, again, back to one of the things that we have been talking about, that demonstrations in Euclid's elements involve, all of them involve a process that Kenneth Manders calls augmenting diagrams. Augmenting diagrams in the sense that this augmentation requires some sort of manipulation using given datum. Once this manipulation is carried out, we can extract co-exact information between what is given to us in a proposition and what we were supposed to demonstrate. These co-exact informations are the ones that not only allow us to carry out the diagrammatic reasoning, but also in the overarching perspective, demonstrate the truth of the proposition. Namely, making explicit the exact relation between the final stage of construction and our initial datum. Exactly like the proof or demonstration of the exterior inequality of the exterior angle that we were just talking about. So, within this landscape, the landscape of augmented diagrams, ultimately what we are doing is that we interpret everything in terms of dependencies induced by construction of co-exact information between our geometrical configurations. For example, a construction a step, the joining of 2 points in a segment, produces an object Y, namely a segment, from a tuple of object X prime, example 2, which are 2 points. Now, if Y and the object X prime are so related, say that Y directly depends on the object X prime, the relation is asymmetrical and so naturally understood as an ordering relation. We can extend it to all objects of the augmented diagram by taking its transitive closure and so obtain a partial ordering that records the dependencies of the diagram's objects. To describe how this partial ordering enters into the interpretation of the diagram, it is useful to define one more term. Define the relation is linked as the symmetrical version of the directly depends, of the directly depends. For example, X and Y are linked if X directly depends on Y or Y directly depends on X. So the problem of isolating the general, the universal, in the augmented diagram comes down to determining which of the unlinked object in the diagram display general relations. The relations exhibited by linked objects are automatically general. For example, a circle and an equilateral triangle. The relations exhibited by linked objects are automatically general. It is built into the concept of a construction step that the constructed object, for example, y, has a certain positional relation to the object x prime it was constructed from. If a line segment is constructed from, for example, point P1 and P2, then it is immediate that this line passes through P1 and P2. Also, if a circle C is constructed from center P and radius R, it is immediate that C contains P and R. Generality or universality in Euclid systems cannot be said to be built into the relations exhibited by unlinked objects in a similar way, however. And so it is indeterminate whether these relations depend on the partition or not. The rules of the Euclidean system that are of central interest are those that remove this indeterminacy for a certain relation and classify the relation as general. So this is the overarching diagrammatic methodology in Euclid's Elements in terms of how constructions link objects or geometrical configurations to one another, and through this act of construction that link geometrical objects, we can make we can basically make manifest the universals or generalities or invariances. And this is very much in tune with Proclus's commentary on basically on Euclid's Elements that I was talking about. You remember we talked about particularities and different levels of universality, and how we move back and forth between universality as such and particularities by way of these intermediating universalities. And these intermediating universalities or generalities are the process of construction in Euclid's Elements, which are carried out by linking via co-exact information geometrical configurations, particular diagrams. Questions?
Just to troll, I guess, like, isn't it a bit presumptuous to think that the result of our construction, or something that we come to through our construction, would be even remotely universal, especially as like acknowledging that the gaps?
Yes, yeah, no, it is. I mean, from the modern perspective, it is promised. It doesn't hold up from the modern perspective. Let's put it that way.
Okay.
But we shouldn't fault Euclid about this. As I mentioned, Euclid's Elements, before even being a mathematical book, is a philosophical book. It has a philosophical ambition. And this philosophical ambition is particularly about the metaphysical status of mathematics, rather than the exact, what you might call to be exact epistemological and structural characteristics of mathematics. So, of course, even if from a modern perspective, we might see this to be a faulty position, but we see that in fact it works. if you completely forget those gaps. The gaps are justifiable within the Euclid systems precisely because the Euclid systems is not a formal system. It in fact never claims to enjoy such a status. It always, all of the, basically every of the primary definitions and common notions are intuitive and are about not exact information about magnitudes as such, but about their comparisons. If we, get rid of the idea of gaps that can only be seen from the perspective of formal mathematics and contemporary perspective, then we do see that in fact it produces universals. And in fact, this is really so what I'm trying to say is that in order for us to look at Euclid's elements properly, within the context of Euclid's time, we should see Euclid's elements as a metaphysical treatise about the status of mathematics. Even though Euclid has gaps at the level of methodology, but at the level of the metaphysical ambition, it gets it right. Yes, this is mathematics. It should be able to move between particularities and pure generalities. Now, whether Euclid's elements can do this or not, it is entirely dependent on the kind of methodology that we are using within the Euclid system. As I mentioned, the diagrammatic reasoning does not allow us to overcome these gaps. Nevertheless, the formalization of the Euclid system, a project started by Tarski, allows us to do this and to show that, in fact, at the level of methodology, once we rectify this, the Euclid system produces universalities. I mean, basically, it lives up to its metaphysical ambition.
Interesting. Cool.
So is that generally, maybe this is just like a trivial question, but is that generally the case that if we formalize a system and invent a fully formal notation for something that previously wasn't, that it necessarily generalizes over gaps, like, for example, the one involving a curved plane versus a flat one, or an unwrapped one, that were present in the non-formal system? Is that sort of like what distinguishes a formal, the gesture of formalization, or a formal versus a non-formal system is generalization versus gaps?
No. You see, what basically the formalization of Euclid's system allows us to do is that it does not, you remember that these gaps were more like hidden assumptions, okay? Hidden assumptions that weren't stated as explicitly within our previous definitions, axioms, and postulates. What formalization does is that it does make these assumptions explicit, precisely by way of well-formed syntax, by way of introducing logical laws, so on and so forth. And within that system, we still miss the whole, the richness of non-Euclidean alternatives, that if, for example, moving to a different plane. But nevertheless, the Euclid's proof holds up precisely because, for example, the hidden assumption that we are working on a unwrapped flat surface has already been made explicit by way of formalization. We don't simply move or overcome the inadequacy of the system, but we simply make the system robust from a formal perspective. Formalization of a Euclidean system doesn't necessitate transition to non-Euclidean system, but all it does is to show that the Euclidean system works, why it works, precisely because there are formal connections.
Right, so it sets up a loop where it makes it clear that in order for the conclusion of Euclid's proof to be true, it needs to be the case that we have this assumption of an unwrapped plane, and that if we have that Euclid's proof correctly uses the assumption of an unwrapped plane to reach the conclusion that it does.
Yes, yes.
Yeah. And so that doesn't really, that there's no necessary connection between at least like the idea of alternatives or like the availability of potential alternatives, like, you know, having a larger space of topology to operate in which to say, we can define what it means for there to be a flat plane, which is not a curved plane.
It's really hard to say, probably not. And that's because you see, I mean, isn't it the whole point of a mathematical system, the point of the whole axiomatic system? So we know that Euclid's Elements is not axiomatic, but let's say that Tarski does this, turns it into a fully axiomatic system, in which the proofs are fundamentally different from the diagrammatic proofs of Euclid's Elements. This creates a system, a system that within itself is always basically what you might call to be its constructive potentialities are always restricted by the kind of building blocks that it has incorporated, namely its axioms. What you might call to be its restriction with regard to possible other alternatives, non-Euclidean alternatives, is always determined by the nature of the axioms. The axioms, if you want to move out of the system, then you need to revise your axioms.
Right.
Basically, coming up with a different system for constructing different axioms. And that system also will be limited again by its own axioms. And then you can see this quite you know, in tandem with Gödel's incompleteness.
Okay, I think I follow that. And then sort of the equivalent of having to devise new systems of axioms, if you somehow wanted to do this like prior to or exterior to axiomatic systems, if you were doing it from the perspective of a quasi-formal diagrammatic proof, sort of the equivalent of moving that into a new kind of underlying space or a new set of hidden assumptions, is there sort of something as, I don't know, as clearly statable as, well, you need to devise new axioms? What is the, well, you need to be able to do this in order to, like, within Euclid's own type of method, move from a flat unwrapped plane to a curved one, for example? Is there sort of like a similarly well-expressed move that you have to make, like, even since you don't have these premises that you can just say, well, I need to rewrite some of these, I need to find new ones in order to move my system into a new basis?
Well, I don't think that there is like a general I don't think that we can come up with general thesis about whether the moves, the transition moves are already contained within the old systems, or actually partially require us to, in fact, thoroughgoingly move out of the previous system. There is no, I don't think that there is a general statement about this.
Okay.
We can't really come up with a, I mean, I really don't know. You know, from the perspective of, for example, Lobachevskian geometry and Euclidean geometry, you can, but I genuinely don't know, for example, what would be the case within other geometrical systems. Are there, for example, are the transition moves, can you identify them within your existing system, or whether you have to completely abandon them? I mean, abandon your system to, in fact, to arrive at these transition moves.
So,
yeah, definitely makes sense. I don't have like an argument here or anything. I'm just kind of exploring this relationship between like gaps, alternatives, and reformulations, like how we are able to make these jumps from one system to the next. But yeah, that's really interesting. Thank you.
But of course, you see, there is, I mean, usually you see alternatives in terms of moving to a new system, not simply, you know, for example, finding an alternative geometrical object, moving it to a different geometrical system. They usually, these identifications happen at the limits, at the higher limits, where basically the constraints of the system within the Euclidean system are really about parallel postulate, where basically you can see what is exactly the constraint of the system.
Oh, okay. As the most compact form, you can see like in the simplest way, you can see either these lines are parallel or they are not, and on that basis, you can see the rest of the sort of the underlying geometric assumptions going on in Euclid. Okay.
Yes.
I think Maria has a good question here too that kind of brings it back to the text.
What was proposition 27 again?
That was infinity, or when the parallel lines.
Oh yeah, yes. Yeah, if you remember, so we talked about this when we were talking about the inequality of the exterior angle. We said that the point F doesn't essentially come inside that angle ACD. And hence we can say that, for example, angle ACF is within the angle ACD, namely part is inside its whole. Now, we have the similar situation with proposition 27. You remember that we were saying that these, if we put them, let's say that they do in fact intersect. Then what would be the result? Then the result would be that the result contradicts the premise of the proposition. The situation for proposition 27 is not quite similar to this, but I mean it is not the same, but it's similar. It's like something like this. Let me. Something like this. This is a perspective, an I. This is a point C, the intersection, and A and B. So this is a very rudimentary form of a non-Euclidean geometry. So what is this exactly? You know, in Euclidean geometry, a straight line moves and should only create one point here. So if you were seeing this object, you can think about it as a straight line just moving to this point C. But point C within non-Euclidean geometry can create 2 points rather than just one on the plane of perspective. And this creates a triangle whose sum of interior angles are slightly more than 180. This is something that it is really interesting that the problems with proposition 27, and hence moving toward the non-Euclidean geometry, weren't fully identified until the advent of Newtonian mechanics. That some of the observation of physics, in fact, led to postulating what you might call to be alternative geometrical planes in which the Euclidean parallel postulate no longer holds. So it wasn't really, for this case, for the case of proposition 27 and how you prove it, wasn't really mathematics that fully was responsible in identifying alternative system, but it was how mathematical physics put forward, in terms of observational anomalies and laws of physics, postulated the existence of alternative geometrical planes in which proposition 27 no longer holds.
So can I just read out sort of this question that I had? I think it connects to like both what Maria and Jake are talking about. It's what are the laws that are governing the creation of new axioms? Is it our goal just to maintain as much of the existing system as possible? How do we move from one axiomatic system to the next? What's the system under which that transition operates?
I don't think that there is a, you see, this question cannot be answered within, with regard to what you might call to be quasi-formal system of Euclid's elements. This is a question that Hilbert tries to answer within his formal system. That's the transition, what you might call to be the moving from one axiomatic system to another axiomatic systems, are done from the perspective of finding axioms, or what you might call to be axiomatic relations that can be said to be more general than what is already within your given system. So the moves, what I'm trying to say is that the moves from one system, axiomatic system, to another axiomatic systems is not discovered just by way of, for example, identifying the upper limits or upper constraints and limitations of your existing axiomatic systems, but needs to be understood within the overarching program of generalization of mathematical structures, with this underlying assumptions that whatever axiomatic systems that you are currently working on, you can still find a more general mathematical structure. So this is, again, really, I think, I don't want to get into too much. So it's ultimately this move from the perspective of philosophy of mathematics has something to do with an assumption concerning the metaphysical status of mathematics, namely the transition between particularities and generalities. Our moves from one axiomatic system to another are warranted by our overarching goal to find more general mathematical structures. And precisely, we see that, in, for example, 1950s, 1960s mathematics onwards, this becomes, the the dominant trend of development of theoretical mathematics. That's the transitions are always being postulated by way of hypothesizing or constructing a more general mathematical structure. That whatever, again, and this has nothing to do with what you might call to be just about, for example, the limits of our current axioms. But it is, we need to think about it also in terms of the, as I said, the affirmation of the of an assumption regarding the metaphysical status of mathematics. That metaphysical status of mathematics needs to be moved toward generalities, and hence, from this perspective, philosophically, you can say that whatever general mathematical structure that you are working with, whether non-Euclidean, Euclidean, so on and so forth, there is always a more general mathematical structure than this. And hence, how can we really generalize any given mathematical structure? Moving, for example, from generalities existing within our current axiomatic systems to a more general framework. This is a process that is done by way of all of the procedures in contemporary mathematics that deal with processes of generalization. The process of generalizations, you can think about it as, for example, if we have a given mathematical structure, introduce some algebraic geometrical operations that can generalize this further. Now, once you generalize this further, your current mathematical structures that hold up within your axiomatic system, then see whether your mathematical system can support this new generality. If it does not, then that's when you can pose or posit, to be more accurate, posit this new generality as a new axiom. A new axiom that combined with new generalities that you have constructed can be taken as a new set of axioms for a different, more general axiomatic system. So this is, again, comes back to this idea that this transition, from one axiomatic system to another axiomatic systems can be seen from different perspectives. From a Hilbertian perspectives are simply, finding the constraints of your systems completely within formal relations between your current axioms, or within a more overarching landscape, generalization of mathematical structures, which is, as I said, which is essentially at its core is a thesis about the metaphysical status of mathematics as such, that mathematics should strive for more generalities, and hence the operation of mathematics should always investigate, by way of operation of mathematics, we should always investigate the level of generality of mathematical structures that are given or within a specific or certain axiomatic system. If we are capable of further generalizing these mathematical structures and then investigating and confirming that the current axiomatic system does not support these generalities as it should be, then we can extract these new general structures and posit them as axioms of a new mathematical system. And in fact, looking into the history of mathematics from the time of Euclid's to contemporary mathematics, we see this is exactly what is done, how the transition from one axiomatic system to another axiomatic system is done by way of striving for broader generalities and testing the limits of current axiomatic systems against the emergence of what you might call to be these new generalities, new general mathematical structures.
So is an example of an axiomatic not supporting a new generality, including like paradoxes or contradictions arising from it? So if we think of like having to introduce the axiom of selection to prevent Russell's paradox from arising, is that a case where we have, like, if we had to add an axiom that restricts your ability to designate sets further than it was before in order to prevent a paradox from arising, is that still like sort of adding an axiom in order to like non-contradictorily support a new level of generality, which is set designations?
Yes. I mean, usually paradoxes, contradictions, what you might call antinomies, emerge precisely because the relationships between axiomatic constructions are not adequate to cover the new generality that we have thus constructed. But also, I think there are different reasons and there are different ways of, for example, identifying that, for example, our current axiomatic system is not adequate to deal with this range of generalities, and that some of these don't have essentially anything to do with the rise of contradictions or antinomies within our current axiomatic system. They are just basically what you might call to be the exactly like, for example, our the difference between the Euclidean and non-Euclidean. It's not just it's not really contradiction. It's that you see that simply axioms and the kind of construction that is licensed by them is no longer adequate for
subspecies.
For accommodating these generalities within their scope of constructive influence.
Right. And then my other question, if everyone will bear with me for just 1 second, is like, so in terms of different species of generality, so you've definitely got, like, I understand they're like in a single line having higher and higher levels of generality, but like in the 20th century, if we look at like set theory, say set theory, category theory, and Gödel numbering, they seem to be three like qualitatively different types of generality or accounts of generality. Is that a different dimension of difference among generalities than the one you're talking about, or a similar one?
I think they are different because the kind of Proclean generalities I was talking about, you might see them as, again, as metaphysically characterized levels of generality. Whereas when we are talking about set theory, category theory, this is not the metaphysical status of generality. It's simply generality of mathematical structure. Category, for example, categorical objects can be seen as more generalized version of set theoretic objects. Precisely because they encompass more exact information.
But so, and you
mathematical information.
You don't think that that kind of higher generality maps to a higher metaphysical generality?
You can, but of course mathematicians are not interested to do that. Not all of them, of course. Good mathematicians sometimes do. I mean, this is like Grothendieck, for example, or Albert Lotman. You know, Lotman was a complete Platonist, and you see that this is exactly what he tries to understand, make a correspondence between the metaphysical status of mathematics and the metaphysical levels of different metaphysical generalities on the one hand, and the generalization procedures of mathematics as such within a completely formal characterization. But this is, of course, I mean, you know, this is something that is more in line with the philosophy of mathematics rather than how mathematicians look at their own discipline.
Okay, that makes sense. Thanks.
Would you be order resets groups categories?
In terms of levels of abstractions, groups being a more abstract level than sets, and you know, and then categories being more abstracted groups.
In terms of generality rather than abstractness.
Okay, generality, yeah, that's what I mean. Okay.
Yes, yeah, sure, yes.
But do me a favor and elaborate on that distinction between generality and abstraction.
You see, when, I mean, from a philosophical perspective, we might say that, sure, generalities, at least from a Platonic standpoint, that generalities are abstractions as such, not abstract, but abstractions as such. Act of abstraction as such, rather than abstract objects, and that's what makes them generalities. But when we are talking about, for example, the between sets, groups, and category, and the concept of abstract in mathematics, the concept of abstract in mathematics is not essentially related to the concept of generality. Abstract in mathematics, I think, for a good part, is about pure, what you might call formal relationships. Formal relationships that are what you might call to be context independent, to be completely devoid of any semantic dimension. And that's exactly, so what I'm trying to say is that, yes, there is a correspondence between abstract and generality. Well, we should be careful when we are talking about abstract in mathematics. This abstract in mathematics can be understood as it is usually being understood in a completely different characterization given by the school of formalism, by Hilbert. That abstract is no longer interpreted in terms of generalities, but simply in terms of pure, complete formal relationships.
Okay, I sort of get the distinction, but still, I mean, a lot of people, for example, will refer to group theory as abstract algebra, when to speak less loosely than you would say, they should say general algebra.
Yes, yeah, abstract in that sense. I think it's more of a relaxed definition of abstract. That's, yes, from that perspective, yes, but it's more of a common sense idea of the abstract rather than what mathematics understands abstract.
So I just want to give you a heads up. We're 10 minutes to 3:30. If you're able to stay longer and would like to, and other people want to stay a little bit longer, that's fine. If not, we can end directly.
I think we are good. And next session, sorry for this connection. I think that the connection got better, but I couldn't turn on the iPad. I will, nevertheless, I will try to cover some of those things. But nevertheless, you can, on your own, look at a couple of propositions in Euclid, particularly look at the demonstration of parallelogram, that the two sides and opposite angles of a parallelograms are equal, and also at the demonstration of, let me see which proposition it is. It's proposition, it's proposition 35 in book 1. It says parallelograms which are on the same base and in the same parallels are equal to one another. Look at this demonstration on your own, and as a kind of a homework, try to specify exactly how many times you use co-exact information. Which steps of your demonstration involve extraction or use of co-exact information in the definition of co-exact that I gave. So that would be kind of homework, and also you will go and investigate what a parallelogram is and learn some of the interesting properties that parallelograms have and make explicit. So that would be homework, and then I can get back to the idea of parallelogram when I'm talking about linear algebra. But next session I will talk about a little bit about this relation between mechanics and geometrical problems, between engineering in medieval times, and not specifically just in Middle Ages, but from Antiquity to late Middle Ages, this significant correspondence between mechanics, engineering, and machines, geometrical analysis, and talk about a couple of examples from Archimedes that then should help us to move forward with Nicol-Orim's diagrams.
And do you have some reading that you might recommend for this week?
Yes, I will put. I have a couple of books on this relation between machines and geometrical principles. I will put them in the Google Drive.
Great.
Okay, everybody, I'm going to go down and join the march. So see you next week.
All right. See you, Philip.
Thank you very much. Have fun.
Thanks, Reza.
Bye-bye. Bye-bye.
Thank you.
Bye, everybody.
Bye-bye.